All engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
Discoveries.
Advances.
Questions. Research.
technology. Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to The Naked Scientists Friday News Edition, where each week we bring you right up to date with what is happening in the world of science, technology and medicine. I'm Chris Smith. On the way, how bacteria could be supercharging cancer cells, the ghost fishing nets laying waste to our oceans, and could capturing carbon underground hold the key to our net zero ambitions?
The Naked Scientists podcast is powered by ukfast.co.uk.
Cancer occurs when DNA is damaged in such a way that cells begin to disregard the normal controls that regulate their behaviour. But in recent years, scientists have discovered that tumour cells may have accomplices that make them more malignant and possibly even resistant to chemotherapy drugs. These accomplices are bacteria, including ones that are normally carried in the healthy human mouth. They've been spotted in a large range of cancers, but it wasn't clear whether they were just there because cancer cells are abnormal and have grabbed some of these harmless bacteria, or whether the microbes are actively contributing to the disease process. Now, Scott Verbridge at Virginia Tech has been able to show that when these bacteria are present, tumour cells behave differently. They grow and move more actively. And not only that, but they can also alter the behaviour of adjacent cancer cells that don't even have any of these bacteria in them.
So there's this bug that is in basically everybody's mouth, and it's been known for roughly a decade that this bacterium has been present in cancers of the gut. They seem to be present in tumors that are worse for patients. More recently, we've started to discover that there are actually bacteria present in all kinds of tumors. So in breast cancers, in lung cancers, pancreatic cancers. We used to think that these tissues should be sterile. And so our goal here was to understand what this particular microbe might be doing that's consistent among different tumor types.
I guess there are two questions here, which is really, is this cause or effect in the sense that are these bacteria there because there's a cancer there and it's just abnormal so it picks them up? Or are they causing this cancer to behave the way it does? And are they playing a role in the progression of that cancer? Because cancers progress, they invade other organs. And to what extent the bacteria might or might not be playing a role in that?
That's exactly right. A lot of the early work was just showing that these bacteria are there in tumor tissues and showing a correlation. People that had more of these microbes in their colorectal cancers would tend to have worse prognosis. But like you point out, that doesn't show that the bacteria are driving the aggressiveness of the cancer. It could just be that the more aggressive cancer is a better host to the bacteria. And so, we were interested in kind of contributing to separating the correlation versus the causation.
Are the bacteria in the cells, on the cells, next to the cells? What's the relationship?
Probably all of the above, but one of the interesting features of these microbes is that they do get inside host cells. And that's really interesting because one of the observations that really drove us down this line of questioning was the bacteria are not only able to get inside of the cancer cells, but they're able to survive inside those cells long enough to spread from a primary tumor in the colon to a distant tumor in the liver. And so that really was the main questions we have. Are those bacteria kind of just along for the ride, or are they actually actively driving that migratory process?
And how did you test that?
We directly infected tumor cells and then measured their migratory capacity. We can watch, in real time how they move, both with and without the bacteria in them. So when we infect the cancer cells, they are more migratory. They move around faster. They're just more active in their movement. They're also more proliferative. They tend to divide rapidly. And the speed at which that happens is greater for the pancreatic cancer cells that have these microbes inside of them. Now, beyond that, what we've also shown is that cells that are next to cells that are infected also have that same set of effects. The cells that are infected are actively spitting out proteins that are accelerating proliferation and migration movement in both the infected cell as well as neighboring cells.
So one cell picks up some bacterial passengers, some freeloaders, that in some way manipulates the infected cell, but makes it then feed all its neighbours, so they all get a growth boost.
That's exactly right. Yeah. So there's kind of a built-in amplification there where you might not necessarily need to infect all of the cells in that tumor. You might have kind of an action at a distance where the infected cells are stimulating growth in the adjacent cells.
And if the bacteria can turn this effect on, have you identified what factors are being turned on? And therefore, if you block those, does the effect go away?
So what we've done so far in terms of blocking has to do with understanding the physical structures that are in the membrane of the cancer cells that the bacteria seem to be binding to. These bacteria like to stick to a kind of a sugar that tends to be overregulated, upregulated in cancer cells. And the bacteria cells have a molecule in their own membrane that allows them to anchor to the sugars that are in the cancer cell membrane. And when we go ahead and interfere with that anchoring process, we can block the bacteria from invading in the first place. So that's where we've gotten a handle on interfering with this process so far.
The question that probably is foremost, therefore, in many people's minds is that we have drugs that kill bacteria. So if we were to give big doses of antibiotics to patients with cancers, would you speculate that that might have an attenuating effect on the rate of progression of a cancer?
It certainly might, and that's something that we're thinking about. There's some really wonderful animal work in colorectal cancer showing that you can actually improve outcomes for mice that have colorectal cancer by treating them with antibiotics that can destroy these bacteria. The challenge is that there's also a whole field of work looking into how your native microbiome, how that population might affect your response to cancer therapies. Some of that evidence seems to show that some of these microbes actually help the therapeutic response. So there are some studies showing that broad spectrum antibiotics that just wipe out everything can actually reduce the efficacy of chemotherapies or immunotherapies. So it's not going to be as simple as just, we want to get rid of all the bugs in our body, because a lot of those bugs are really helpful.
It's a fascinating study, isn't it? Scott Verberidge there, and he just published that work in the journal Science Translational Medicine. Now, despite the best efforts of British politicians at the moment, climate change does remain high on the news agenda. Extreme weather is happening increasingly more often around the world, and the finger is pointing firmly at global warming as the cause. Each year, us as humans pump out the best part of 40 billion tonnes of carbon dioxide into the atmosphere, and the amount that's already accumulated up there adds up to a dizzying trillion tonnes or so. So, cutting carbon emissions is a priority, and the UK may be blessed with a very effective way to do it, by storing it deep underground. This week, the Royal Society have published a policy briefing on offshore carbon storage wells. It's titled Locked Away Geological Carbon Storage, and it details the viability of processes to permanently store carbon dioxide in deep saline aquifers and old offshore oil and gas sites. James Titko spoke with the report's chair, Cambridge University's Andy Woods, asking him first why we even need to do this if we're moving towards net zero forms of energy generation like wind and solar.
There are parts of the energy system where it's very hard to decarbonise, particularly in industry. So in cement manufacture, in fertiliser manufacture, and in iron and steel manufacture, there's a lot of carbon emissions as part of the process of making those products. And so one solution is to capture the carbon as you produce those products, and then that carbon can be compressed and pumped and then stored in deep saline aquifers offshore. There's a couple of projects being developed at the moment in the UK. There's the Net Zero Teesside project, which is planning to capture a whole series of carbon sources and pump them offshore and store them in a reservoir 1.5-2 kilometres below the seafloor in the North Sea.
So can you go into a bit more detail on that? What does geological carbon storage look like? How does it work?
These streams of carbon dioxide, they're compressed and it becomes a very dense, high-pressure liquid with a density close to but a bit smaller than the density of water, and that's injected into these sandstone layers about 1 to 2 kilometres below the seabed. Typically, the geologic strata isn't exactly horizontal, but it'll have highs and low points. And if you can find a region where there can be some trapping, if you put the carbon dioxide into that, it'll float on top of the water in this sandstone layer. And you'd be looking for one where there's a shale or some other very low permeability, low conductivity rock above that'll trap the carbon dioxide in that store. that gives you what's called structural trapping. And then over time, the carbon dioxide is soluble in the water in this saline aquifer, and so it'll gradually dissolve into the water, and that'll increase the sort of integrity of that storage.
You mentioned before a couple of the projects already underway. What's the aim then with publishing this report? Is the UK going to be able to perhaps position itself as a real player in geological carbon storage?
So what we wanted to do is actually focus on the storage side of carbon capture and storage, and just look at the technical and engineering challenges and the science that's needed to drive this technology forward, but also to identify how big a part of the energy transition that this will be. So the IPCC have projected that we'll need to store between about 300 and 1,000 gigatons of carbon by the end of the century. And just to put that in scale and a reference, if you look at a net zero energy system, the International Energy Agency have a model about what a net zero energy system looks like in 2050, and that will include carbon storage, storing about 7 or 8 gigatons a year, and that's about 20% of the total emissions that we produce today. So it's a very large fraction of the total carbon emissions, and that requires a scale up of our carbon storage potential from what we have today, which is about 40 megatons a year, up to this 7 or 8 gigatons a year. So that's scaling it by a factor of 200. And so the purpose of this report was really to highlight to policymakers the great potential of this carbon storage as a very important part of the energy transition, but also to alert them to the need really to scale up investment and regulation and the policy framework to actually accelerate our implementation of carbon storage. And for the UK, this could be a major source of growth and a major new industry that we could develop with huge potential to export the technology and the technical solutions, as well as storing lots of our own carbon emissions.
Andy Woods. The planet has an estimated 60 million fishermen, and they use nets strung between boats and across rivers, long lines armed with thousands of hooks, trawl nets that get dragged across the seafloor, holding pens for aquaculture, and of course good old-fashioned crab pots to catch their fare. And together they feed over 1 billion people. But in the course of doing that, massive amounts of gear goes overboard, contributing to huge environmental impacts. And the scale of those losses, which Denise Hardesty, based in Hobart with Australia's CSIRO, has now managed to calculate, and will almost certainly make your eyes pop out.
So we set out to ask how much fishing gear is lost to the world's ocean. So we went out and spoke with fishers in 7 countries around the world and using a lot of different types of gear. So we asked fishers who fish with fishing line, like long lines, with different types of trawl nets or fishing nets that are designed to catch your fish in that way, and also with pots and traps. So we really spanned the full breadth and depth of the world's commercial fisheries.
And is the metric then, you say to them, how much gear do you buy in a year? And you assume that what they are buying is to replace what they've lost?
It's not about asking the fishers, how much fishing gear do you buy each year, and then subtracting out how much is lost, because many of the fishers that we interviewed, they're not the ones that own the companies that are making those decisions. What we did instead was ask the fishers, how long do you spend at sea? How much gear gets lost? How often does it get lost? When and why and where? Under what conditions do you lose that fishing gear? And then we coupled that with information about how much fishing effort happens around the year from an independent data set. And that allowed us to match or to marry those 2 really different types of information together to make that estimate of how much fishing gear is lost to the global ocean.
And how much is?
So for one single major fishery a year, around 740,000 kilometers of fishing line alone is lost. And with that are 14 billion hooks. If you want to put that in perspective, that's about circling the Earth more than 18 times for that fishing line, or going from Earth to the moon and back. We also estimate around 3,000 square kilometers of gill nets, 75,000 square kilometers of another type of net called purse seine nets, and over 25 million pots and traps each and every year.
Of course, many of these are man-made plastics and polymers, aren't they? So they're going to be adding to the global ocean plastic problem, but they're not going to go anywhere. They're just presumably going to build up in the sea somewhere.
So they're going to fish indiscriminately, and we call that ghost nets when these abandoned or lost commercial or other fishing nets are lost at sea because they just continue to fish indiscriminately. And what this means is they're catching fish, they're catching turtles and whales and dolphins and, other marine mammals, costing lots in terms of biodiversity impact, as well as having quite a substantial potential impact on the global fisheries and on global food security. Because if we capture these fish and they die in the nets, but they aren't making it to people's dinner plates, then we're actually not able to utilize not only the protein benefit, but the economic benefit from fishing.
My mind is boggling with these numbers that you're coming up with. This is quite terrifying in terms of how much is therefore out there. Do we actually have evidence that this build-up is doing, as you say, and having a knock-on effect on species and so on?
Well, one thing that we know from some previous work on looking at ghost nets in one particular part of Australia was we estimated that around 10,000 turtles a year are killed or captured by nets just in that particular area. So we do have evidence from that study and from other separate bodies of work from other researchers around the world that have highlighted particular problems in particular small areas. What we've done now is really show what that looks like at the global scale in terms of how much is lost. And you said that's really confronting. And when we think about it, that's 25 million pots and traps each and every year, 14 billion hooks each and every year. So, this is adding, this is accumulating in the oceans, and it's also getting cut up on sensitive coral reef beds. It's getting washed ashore and damaging sensitive marine and coastal ecosystems and habitats such as mangroves. It's smothering our reefs. It's causing quite a lot of damage.
What can we do about it? When scientists back in the mid-1980s spotted an Australia-sized hole in the ozone layer over Antarctica, very promptly they were able to galvanise action. They got the Montreal Protocol together. We banned CFCs as the cause and hopefully have arrested the progression of the ozone hole. What can we do about this?
Well, that's a really great point. So what can we do? I think the first thing to do is to not only understand how much is lost out there, but to also really unpack why and when that fishing gear gets lost. And so that's what we did. And what we find is that smaller vessels on average lose proportionately more gear. We also find that fishers that are fishing on the bottom of the ocean tend to lose more gear than those fishing in the midwater or on the surface of the ocean. And we also understand a bit more now about why and when we're losing gear. So when there's bad weather and fishers aren't getting that much money, they tend to fish in marginal conditions. As we start to see a reduction in the amount of fish in a particular area, we may have more fishers crowding into fishing in a smaller area. And that means we can see conflicts between different gears and between different fishers. And when there's conflict, when lines or nets run over one another, they may end up getting caught or tangled and being cut apart. And so some of the things that we can do is to ensure that fishers have the best equipment possible. We can look at potentially incentives to reduce fishing gear losses. And so we can provide buyback programs or low-cost loans for fishers to replace their gear before they're so close to end of life that they're likely to get lost.
So when fishermen talk about the one that got away, it's also the nets and lines that we need to be thinking about, isn't it? Thanks very much to Denise Hardesty. She just published those findings in the journal Science Advances.
Much has changed for business owners, managers, and staff recently. But with over 30 years' experience in telecommunications, award-winning independent company Spitfire have the expertise to make sure you stay ahead and can keep on innovating. Whether it's connectivity, MPLS networks, firewalls, or phone systems, Spitfire can help. To find out more, go to spitfire.co.uk. That's spitfire.co.uk. Spitfire, telecoms and IP engineering solutions for business since 1988.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith, and on the way, what DNA is revealing about Neanderthal society. But first, A plan to alleviate the logjam in UK general practice by loosening access to antibiotics so pharmacists can prescribe them has had a febrile reaction from doctors who described the plan as risky, worded as it was to suggest that it would make it easier to access more antibiotics for more ailments. The Department of Health, on the other hand, estimates that about 1,000 of England's 27,000 pharmacists have a prescribing licence, and that chemists prescribing antibiotics for instance, urine infections alone, could free up about 400,000 GP appointments every year. But the message was somewhat tarnished, according to a report in the Times newspaper this week, that discussing the move, Health Secretary Therese Coffey had remarked privately that she had handed out her own supplies of antibiotics to friends and family who were feeling unwell, attracting widespread condemnation from the medical profession, who called her reckless. So what's right and what's wrong with all of this? Well, Nick Brown's a consultant microbiologist and an expert in antibiotic resistance who sits on the British Society for Antimicrobial Chemotherapy Council.
The recent interest in access to antibiotics has come about because of a statement this last weekend that people will be able to go to their local pharmacy and pick up antibiotic prescriptions there without having to go to their GP. And this, of course, is one initiative that has been proposed to get around the problem of people having to wait a long time to get a GP appointment.
But what Therese Coffey also said was, I dished out some old antibiotics to a mate, which many other doctors, I think quite rightly, objected to very, very forcefully.
That is correct. And I think every medical professional would not accept that this was a reasonable thing to do, and that people should not share their antibiotics with anybody else. Antibiotics are a very precious resource, and we should use them wisely. Part of that means that you should not give them to people who have not been prescribed them. These are prescription-only medicines. That is a legal requirement. Therefore, you should only access antibiotics by getting them prescribed by a licensed medical practitioner.
The legal side of it aside, why is that bad practice with respect specifically to antibiotics?
Antibiotics are absolutely fundamental to the practice of modern healthcare. Without antibiotics, you could not have a hip replacement. You could not have cancer chemotherapy. You could not have an organ transplant. The problem with antibiotics is that the more you use them, the more likely it is that the bacteria will become more resistant to them. And that means that the more you're exposed to an antibiotic, the less effective it becomes. That is unlike any other medicine. Paracetamol is always paracetamol, and a drug for high blood pressure is always a drug for high blood pressure. But the more you use an antibiotic, the less effective it becomes. And that means only using them or accessing them when there is absolute need to have them.
Why did she start talking about this in the first place, though? What was the general direction of travel that this became an unfortunate diversion for?
The statement last weekend was prompted by the national issue with GP capacity at the moment, that many people are having to wait for several days or even longer to get a GP appointment. And by increasing use of local community pharmacy capacity, potentially people will be able to get a much more prompt prescription of an antibiotic should it be required.
Is that altogether safe, though? I mean, are we comfortable that people would effectively be bypassing the doctor to get antibiotics? Because at the end of the day, a doctor's a doctor and they know what to treat with what. It just seems a little bit of a short change mechanism, corner cutting.
Yes. Now, the important bit is that there need to be appropriate safeguards around that prescription. And there are already a lot of examples of where this is being done very successfully. For example, many minor injury units, senior trained nurses can prescribe antibiotics for some conditions. And in Scotland, there is an initiative called Pharmacy First, which has been going for some years, where pharmacies already can prescribe antibiotics for some limited number of conditions with appropriate safeguards being put in place. The statement from last weekend seemed to imply that this was about increasing access to antibiotics, which it should certainly not be. In the situations in, say, minor injury units or in the Pharmacy First initiative in Scotland, the number of indications whereby a pharmacist or a senior nurse can prescribe an antibiotic are actually pretty limited. and the detail of the patient group direction, which allows them to prescribe, has numerous exclusions on it, which adds another layer of safety. People should only be prescribed an antibiotic in a pharmacy or in another setting if they have a simple infection that is not complicated and therefore can be managed appropriately in that setting.
Nick Brown. So finish the course and don't share your drugs with other people. These days, the human race comprises a single species, Homo sapiens. But until about 40,000 years ago, we shared the planet with a related but distinct group called the Neanderthals. They were so similar to us that the two groups periodically interbred, which is reflected in the fact that 2 or 3% of the DNA in the average person today is Neanderthal. The reason we know this is that scientists can read and rebuild the genetic codes present in ancient remains. In fact, that is what won this year's Nobel Prize for Medicine. But previously, we had only a handful of these specimens to go on, so our understanding of how Neanderthal society was organised and how these people moved about and lived, all of which you can deduce from the genes that they carried and passed on to their offspring, was very limited. But now an incredible discovery of the remains of a Neanderthal community in 2 caves in Siberia has opened a window into this world for the first time. Trinity College Dublin's Lara Cassidy, who specialises in reading ancient genomes, wrote a commentary on the new discovery. These days, the human race comprises a single species, Homo sapiens. But until about 40,000 years ago, we shared the planet with a related but distinct group called the Neanderthals. They were so similar to us that the two groups periodically interbred, which is reflected in the fact that 2 or 3% of the DNA in the average person today is Neanderthal. The reason we know this is that scientists can read and rebuild the genetic codes present in ancient remains. In fact, that is what won this year's Nobel Prize for Medicine. But previously, we had only a handful of these specimens to go on, so our understanding of how Neanderthal society was organised and how these people moved about and lived, all of which you can deduce from the genes that they carried and passed on to their offspring, was very limited. But now an incredible discovery of the remains of a Neanderthal community in 2 caves in Siberia has opened a window into this world for the first time. Trinity College Dublin's Lara Cassidy, who specialises in reading ancient genomes, wrote a commentary on the new discovery.
This is really big news because we've never had data like this before. The authors have sequenced ancient genomes from Neanderthal remains in Siberia. Neanderthals are a sister species to our own species, Homo sapiens. They were living in Europe and surrounding areas around 40,000 years ago. They have managed to sequence 13 Neanderthal genomes. What's really special about this is that they're all coming from in and around the same time and the same place. And that allows us to explore relationships between these individuals.
Where did they study these ancient peoples then? When you say there's lots of them together, it does add a huge amount of data. It nearly doubles the number of specimens we've now got genomes on, doesn't it? But where did they all come from?
These individuals are coming from archaeological excavations in the Altai foothills in Siberia, where we have 2 nearby caves, Chagarskaya Cave and Okladnikov. What they think is that at least some of the individuals they sequenced were contemporaries, so they lived at the same time. Really incredibly, they found a father and daughter pair, and they also found second-degree relatives like an aunt and a nephew or a grandchild and a grandparent.
Were these individuals buried there then? Is that why they happen to have this grouping and they're closely related both in space and time? Or were they wiped out by something? Do we know?
We don't quite understand why their remains ended up in this cave. The cave itself was a campsite. They were processing bison. They'd go down, hunt bison and bring the remains back to a cave. They were also making tools to do that work.
And have we got dates from the local stratigraphy, the layers, to tell us roughly when those people were doing this?
The layers of activity are dated to between 59 and 51,000 years ago.
What does this enable us to infer about Neanderthal society then? Because this is a special case. We've got a large group who are closely related. They're all living together. This is almost like a community. So what can we infer about the community and society in Neanderthal times from these DNA codes?
I suppose there's two conclusions this study drew. The first one was that all of the individuals they could test, they had high levels of background inbreeding, quite extreme. I think the closest modern day comparison would be what we see for mountain gorillas. Mountain gorillas are an endangered species historically. There's been fewer than 1,000 individuals in the wild, and they live in quite small community groups, maybe 20 or so individuals. Our Chagarskaya Neanderthals, they're looking like there's similar demographic dynamics going on there, that they're living in fairly small communities. So that's very interesting, because I suppose we compare that then to our own species, Homo sapiens, because one of the things we're very interested in is how we differ from Neanderthals, because those differences might tell us something about our own species evolution, why our own societies were so successful in terms of dispersing across the globe while the Neanderthals fizzled out. They don't maybe seem as well connected to one another as modern day hunter-gatherer societies that we have now.
It won't have escaped the attention of listeners that time that you're talking about is not far upstream of when this particular lineage went extinct. Neanderthals disappeared about 10,000 years after this. So could it be this is already them in decline, or could it be that they disappeared because of this sort of thing, this inbreeding?
Neanderthals lineage first starts to emerge about 400,000 years ago. So they were survivors in that way. They were in Europe for a long time, and they went through a lot of harsh climactic downturns and then re-expanded again. So I would say there isn't a reason to think that, this type of small population sizes were a sign of sort of their imminent demise. This is a very debated thing about why Neanderthals disappeared. But I think the most kind of popular theories at the moment are more of a demographic one, that they were just simply swamped by Homo sapiens coming in.
Us, in other words. What was the other point? Because you said there were two key learning points in this. One was this small population size. What was the other?
It also seems there is a migration between communities, but the authors propose that this is primarily females dispersing, so leaving the group from which they were born and moving to a new community.
Is that because the males are going off and getting wives, or is it that the women are on the move and joining other communities? Is there anything that we can learn from anatomically modern human societies where there are similar practices?
Yeah. We can't say the exact dynamics. We don't know how similar Neanderthal social organization was to our own. So we wouldn't want to kind of project too much from what we see today in modern hunter-gatherer societies onto a different species of human. Another thing we can look towards is our closest living relatives, which are the African apes. African apes do show female bias in dispersal. Females move between groups more than men. Some people have used that to argue that this female bias dispersal was the ancestral state. That's why actually trying to jump back in time with ancient genomes and understand what was happening in other species of human is so important. We still don't know how flexible Neanderthals were. Maybe if we sampled another community from a different time, from a different place, they'd show male-biased dispersal.
It's a lovely story, isn't it? Lara Cassidy commenting on the work published this week by Lauritz Skov and his colleagues. And that is where we have to leave it, unfortunately. But do join us next time when we're going to be aboard Sea Monster, the retired oil rig that's been repurposed as an art meets science installation. We're going to be there to drill into the circular economy and the science of recycling. To get in touch, the email address is chris@thenakedscientist. You can also find us on Facebook and Twitter. And if you enjoy these programmes, do please consider supporting us with either a one-off or a regular donation, which is a huge help and keeps the show on the road. You can do that quite securely and safely at nakedscientist.com/donate. We're based at the University of Cambridge's Institute of Continuing Education, and we're supported by Rolls-Royce. I'm Chris Smith. Thanks for listening, and until next time, goodbye.